Look, where there's critical or sensitive data, it's going to be relevant. So, of course, financial services, banks, insurance companies, where they're archiving data for decades, and it's also getting harvested now, we really have some focus there.
The migration to post-quantum cryptography is about to begin and is necessary to protect against the threats of fault-tolerant quantum computing. However, critical assets like those in military, banking, and government environments also require other layers of security and strategies, such as zero trust and increased encryption bit sizes. Learn about one high-performance encryption solution that provides such defense in depth today, and will do so after thousands of logical qubits arrive, in this episode of the Post-Quantum World. I'm your host, Konstantinos Karagiannis. I lead quantum computing services at Protiviti, where we're helping companies prepare for the benefits and threats of this exploding field. I hope you'll join each episode as we explore the technology and business impacts of this post-quantum era. Our guest today is the co-founder and CEO of XSOC. Richard Blech, welcome to the show.
Hi, hello. Great to be here. Looking forward to this.
Yeah, this should be fun. Our listeners have heard, of course, of the coming NIST standards and the need to migrate away from RSA and other ciphers. This is the post-quantum world, after all, definitely something on people's minds. But your company handles a lot more than the quantum threat. So to start at like a high level for listeners,
Sure.
What differentiates your solution from just plugging in like new ciphers?
Sure. So XSOC is actually an acronym for something like everything in the tech industry. It's extensible, secure, optimized cryptography. So what we've set out to do back in our founding in 2018 was really to think from the classical side of computing. The post-quantum aspect of it came about just because of the design and what we're doing, since our focus is on symmetric cryptography. So with that, we've been able to design crypto systems and other cryptographic systems around key distribution and security and other aspects in a infrastructure where we have optimized cryptography. Some of those being building blocks or primitives and standards that we've put into what is a crypto system. When I say crypto system, we're not just talking about an algorithm or a cipher. Though there is a cipher, there is more around that. So what we've done, and this is, again, speaking from the classical compute side, is have this very high-performance cipher core, encryption engine, if you will, that delivers performance, security, and lightweight footprint with symmetric cryptography. This part of it, I would say the crypto system is a hybrid of a stream cipher like Cha-Cha-20 and has block cipher characteristics and attributes such as an S-box that help alleviate some of the weaknesses that are inherent with your typical stream ciphers. This has all been through cryptanalysis and, of course, testing and R&D, and that's why it takes the time it takes to really put these together. The encryption cipher, by the way, the core has been put up on GitHub for academic review, but where we put all the muscle into this, where it becomes a differentiator, and why it can be used now while the NIST standards are getting approved, which is really an asymmetric side, is that we put various interfaces that handle all the use cases pretty much that the industry could think of or want to deploy. And those interfaces are in the form of, user accessible, that they would invoke through a command line interface in the form that it's now, or the original form, which is a Java SDK, small footprint, 235 KB on disk. The code base entirety of it is 4,000 lines of code, so very small, tight. And you can operate this from a command line interface in Windows, Linux, or Mac, even ARM processor, really cross-platform. And with that, with 2 lines of code from the CLI, you're up and operating, and then you choose your various functions and use cases and parameters. You can encrypt a string, you can encrypt a stream, or you can encrypt text, voice, whatever that may be. And then you have all kinds of other choices to use that allow for security now in classical compute. And because of the strength of the key or the cryptographic security that we built into the key, you have a post-quantum security properties as well. I'll stop right there for the moment just to let you follow up.
Yeah, absolutely. And we're going to dig into like the different components and how it works. But I thought it'd be fun, instead of just continuing on with like drilling in, to just immediately give people an example of how, even now, before there's technically the quantum threat, right, actually happening, although you have Harvest now decrypt later, there are breaches that happen all the time. There are things that go on now in the security world. I thought it would be fun to just take an example of like a recent high profile breach maybe, and then if you can like walk us through how there could have been a different outcome if something like XSOC solution was in the mix.
Yeah, I mean, there's a few. I mean, I would cite not one that's not as recent, but not that far back, is of course solar winds. I mean, that's affected everybody. So, there would be impact there for sure. Just to touch on that, there would be, there were things that we would do from access control side because, again, the XSOC key, where there's a real differentiator, just to stay at a high level, it has MFA credential capability within encryption key. There's enough space in the XSOC key that allows for knowledge factor, possession factor, CAT card, PIV card, YubiKey, whatever it may be, and biometric, and machine inherent, CPU ID or some other device ID, to be integrated into the encryption key itself, meaning there's one key without reliance on PKI or other asymmetric standards, that you would have an MFA-enabled key. That means the decryption could only occur to the authorized, authenticated, validated party. That thereby, I believe that would not have occurred, or certainly would have mitigated a significant level of that breach. And a more current one, Sencora, is kind of a similar circumstance. That was a big one. And again, it's all this access control. I mean, encryption does so much. There's reasons why you don't encrypt, which are inexcusable to from an XSOC perspective. And but a lot of it ends up being implementation detail and human errors why these breaches occur. And so we think we built something that's a little bit easier to deploy and use, which is a big factor. And then adding the MFA credentialing in, which is where a lot of these breaches occur, is getting through access controls and getting to where the data is residing, and that's where the compromise occurs. And we think we've developed a solution that at least can mitigate much of that.
So in many ways, this solution kind of solves a lot of the things you worry about in security, in tightening down security in, let's say, an organization. Because you're not going to use this shop at Amazon, probably, right? This is going to be like something a company would roll out. It would strengthen security, and it just also happens to be post-quantum safe as well.
That is correct. And it's because, again, just to touch on it quickly, with symmetric cryptography, it's not prime factorization computationally based. It's about key length, and the known attack against that is Grover's algorithm, which basically with a quantum computer would half the key size. So the standard out there now is that the key length must end up being 256 bits of security. That could change too, because we don't know yet.
Yeah.
So we started at 512, and we did it at 512 because because we're efficient. We're faster than AES, even with hardware acceleration that AES enjoys. We have a software solution that outperforms AES even at large key lengths with large files, significantly 8 to 10 times faster. So because of that, we can go with these large key sizes, and that has that post-quantum security just because of that. There's other factors too, but that is the main one.
Yeah, in a bit, I want to dig into how you handle keys, because I think it's actually kind of interesting. So
Sure.
We'll focus on that. So to help listeners understand the approach behind this type of defense in depth, maybe we can go through it in like layers. So as a guide to what's coming, I'm thinking of it as like data at rest, data in transit, and data in use, right? And they're all kind of like different pieces here. So if you can maybe walk us through that, like how it starts, how each is impacted.
Again, it's a crypto system that is meant to have the tools available that you can work on all the different data types in flight, at rest, and of course, like you say, in use. And that is again set by the parameters you decide in the where you want to set out for your particular use case or in your environment. So the way we start anyways, right off the bat, is all about the entropy. Entropy is, a key ingredient to strong encryption, of course. And in software, it's CSPRNG. That is a standard that's available. We just pull from the Java library, CSPRNG, in the case of that. We've also adapted the crypto system to intake entropy from any quantum source for QRNG. Could be a diode, laser, light, whatever that may be, that provides that randomness. So from there, we get strong entropy. So we're starting off right away before anything else happens. Then we initialize the encryption job in less than a millisecond. So that's why we have a big step up in performance, because the initialization is so rapid. And then on the actual encryption, there's only a few cycles per byte. So, everything is moving efficiently. So if we work on a data at rest, that's just a choice. You choose your parameters, and you're going to pick a large key, for example. And so our key sizing goes 100 increments up, not because it needs the strength to go up there, but just so you can have choices and you can set parameters, and you can have more randomness or variableness to your choices. So we can go 100 increments up. That means 51,200 as a full key space size. The key is static. It stays static, 23 KB on disk, regardless of the strength inside. It's dynamic inside the key. Inside the key, there's a delimiter algorithm that when you move the key size up, there's more secure key material and less padding. If at the 512 bits of cryptographic key strength, you have that in the key, and the remainder of the key space is filled with padding and obfuscation. An adversary does not know where the secure key material starts and ends and the padding starts and ends. And even if they did, they would have that security strength to deal with. So this is just an additional factor of another point of difficulty for an attacker to go at. But we can also modulate the key as well. But that's for the second part of the use case, just to finish on data at rest. So you could choose a size of, say, 2048 or 16,400, and that's your data at rest key. And for archival use cases, or you're an insurance company or financial service, you're storing data for 40, 50 years. That's all going to be usable data. There's data harvesting going on now. You want, encryption strength in there that you don't have to pull down in 10 years and have to re-encrypt everything, because that's quite a job. I mean, nobody wants to do that, and you may have to do that by mandate or regulation. So let's start off right away and encrypt at these large key lengths, because it doesn't affect your performance. You're going to be able to decrypt just as rapidly as you could if it were a smaller key. It affects nothing on the performance for that. So that's that use case. The data in flight, because it is part a streaming cipher, we can encrypt a video or a voice stream or whatever at every packet of data. If you chose to rekey at every packet, you could do that. We could rekey every nanosecond with a different key size, a different unique key, and you can change the strength as it goes down the stream. One of the important factors of the streaming encryption that is real time is that it has a self-healing feature, or what we call spin forward. So it has 100% reliability, and there's no packet loss. There really is no packet loss, because the crypto system knows to catch up if wherever there are dropped packets. Now, in a voice call or video, that's not that important, because you're not going to notice that in a voice or video call. But data at rest, if we have one packet missing, that the whole file is corrupted, you won't be able to,
Yeah.
to use it. So we need to have that reliability. That was thought out, and we put that in. And then, so that's streaming video, live video. We have fidelity across. There's no effect on the video quality in a real-time stream until you get way into the upper bounds of the strength. Then there could be a little jiggle, but we've tested all the way up to 16,400 bit strength, and there is 100% fidelity with the video quality. So and sound quality as well. Now, for data and use, that's always the tricky one, because there's a lot of marketing hype around homomorphic encryption, and I've used the term pseudo-homomorphic when I've discussed data and use. So what we are really saying with that is, because we have a database solution too, where we have a mode that is a headerless mode that allows us to encrypt in database, SQL, vector database now for AI, where we're not appending any header that adds any overhead or encumbrance to the data that's being encrypted. So we can encrypt at the column, row, and cell level of a database. However, there's metadata that's still existing. With that metadata, we're able to query the database. Say you have all the data in an S3 bucket, for example, in AWS. You can then query that database from a backup file of somebody's workstation at your facility from 3 years ago, and you need to just pull a file down. Rather than decrypting at the database level or pulling a whole bucket down, you're just pulling the file down encrypted, and then you're decrypting it to work on. So that's why I say pseudo-homomorphic, because you can query it and find it and get it and retrieve it and bring it to you. But when you actually have to work on it, like write text, you're not writing it while it's in an encrypted state. I mean, unless you've got eyes that can read ciphertext, you're decrypting at some point. But
a little matrix moment there.
Right.
I can see it in the code. So yeah, it's really important, because obviously that brings in discussions about roles too, like role-based security. You really shouldn't have everything, right? Depending on what your role is, like you might just need one kind of file and what you have access to decrypt and read. So how does this work a little bit with something like AI vector embeddings? What's the security threat that you're fixing there?
Well, to me, and then I say this also with the convergence of quantum computing coming. Put those two together, and wow, maybe you have something that's not even thought of. How the world and the market has changed. It's always evolving with technology. It was just a few years ago, quantum computing was 15 years away. Now it could be right on the horizon or just a few short years away. And even then, a few years ago, no one was talking about AI, as much with working with quantum computing. So, now things are changing. This is what happens all the time. So the threat on the vector database level, I mean, that's the heart, that's the core of everything that's going to be AI. And okay, it's great to have ChatGPT, and you go in and you can ask questions and it can write some things for you. But now with AI going to be involved in daily lives of everything, and all these military operations and drone technology, something that we're working on extensively, these are going to be personalities that are going to be out there functioning in the world. And we as a society are going to rely, in some cases, on emergency services, on what AI determines. If that gets poisoned or corrupted or interfered with in any way, even with split-second timing, this could be not only catastrophic, it could be cataclysmic because of the chain reaction of events that could occur. I mean, just thinking on a large scale, what can happen if you start disrupting, AI in its objectives of what it's supposed to do, and you change what it was going to do? It's like the butterfly effect, so to speak, just to put it in a high level like that. So protecting it at its core, where you can encrypt, and it takes complete lack of latency to interfere, because everything is about timing, or any encumbrances. You want all integrity and fidelity at all levels. So with our what we've developed with our crypto system and ability even to deliver keys efficiently, that allows for us to be encrypting at that level. And we believe we can be an anchor core, securing the vector database and its embeddings, storage level, storage layer, application layer, and that will significantly enhance the security posture for AI, is what our position is.
Yeah, and if you're doing something critical with AI, like, I don't know, piloting, automated drones or something, maybe you don't want a good look at what that looks like. Maybe you don't want to offer that to the world. It could get literally deadly, or it's
Exactly.
yeah, it's a pretty scary thought. So I can see the benefit in that. So I want to dig a little bit into the symmetric encryption and how you handle key distribution. So obviously the idea, let's give an example from QKD world. You set up your BB84 protocol or whatever, you have your photons of light, and through the establishment of a classical channel also, you agree to build up key data in QKD. You transmit these photons and you end up with a key. That's your key. It's a one-time pad, but it's small, it's slow. So you take that and you use that to send what's going to be the key to the symmetric encryption, which will then be what you transfer. So that's how you do it with light. So how do you handle key distribution in a secure way with this setup when there is nothing like a light channel that will detect quantum weirdness happening and you have to throw away the key?
Exactly.
This is just basic bits running over a wire, right? So how do you handle the key distribution?
So there are a couple methods. There is a key distribution system solution, and then there is without that. I'll explain the first without that, because then it's just a matter of however you want to deliver the key. And that is with the key I was explaining previously with the MFA enablement. If you have enabled the XSOC key and you have injected those three factors of authentication into the key, and by the way, the key is large enough that you could have multiple parties using the key and reusing the key. So your credentials, MFA credentials, can be in there, mine and others, and you could share that key with those parties, and decryption can only occur when you are on the device, have the physical factor, and have the knowledge factor. So you don't even need an HSM, and you can just deliver the key. Yes, it's an extra step. Yes, there's enrolling, but you can do that and not have to involve any additional secure key distribution system. For those that don't do that, a solution for delivering symmetric key, and this could be any symmetric key, not just an XSOC key. That's how we built it. It's default to XSOC, but we could take in any symmetric key. What that does then in our system, it's called socket, is it takes that key and then it contorts it into a 3D object. So we get geometry involved here. That key then spins at a certain speed, variably different each time, and it pitches and it yaws. The calculus of that is put on a primer. The primer goes with the ciphertext, and the key is basically exploded into shards. Those random shards are distributed around an RF, for example, ad hoc, air-gapped environment, doesn't matter, LAN environment. We've used this on Raspberry Pis even, so low power, low compute. There's no storage of any key shards. They're just pinging around an RF mesh network and then get recombined. All this happens in milliseconds at the endpoint, which is authorized and authenticated with those three factors, because it has to go to an endpoint, and the endpoint needs to be authorized. So that's how we securely deliver a key in a LAN environment. Because we built in a protocol called Encrypted Broadcast Protocol, which has a UDP backbone, we are able to unicast, multicast, and broadcast that key in that network. If we're going to use the internet, then that same model can be exposed on a global basis using DHT hash tables in a peer-to-peer environment, meaning anonymous nodes get that key material and ping it around the globe, all again in milliseconds, and then it goes to its various endpoints for authenticated decryption.
Because in many ways, there's not much you can do with those shards if you're not one of those devices anyway.
Yeah, it's a 0 point a failure solution. You cannot. There's nothing you could do with it. I mean, you have to be on the machine, on the device, and have those factors there. It's
because of the hardware.
I mean, you could think a much more secure or N-tier Kerberos is really the way some have looked at this, what it really is. Much more efficient, of course, too.
That's very cool. And so how does that kind of approach affect performance? It sounds like it really doesn't, right?
No, I mean, it's just really built to move as fast as the internet. I mean, it's if you're using the global one and in a mesh network, I mean, you're right at the network speed. So whatever the network is, we're working at.
So what types of companies and sectors would benefit from this?
Look, where there's critical or sensitive data, it's going to be relevant. So, of course, financial services, banks, insurance companies, where they're archiving data for, decades, and it's also getting harvested now. You really need to have, we really have some focus there. Military, government, of course, there's been significant uptick in focus on drone technologies, drone operating system, AI involvement in drones. Now for drone communications, this is the way the new warfare is going to be going. Less human on, boots on the ground involvement, more autonomous machinery involved, drones, ground vehicles, whatever that may be. Well, this is all just like our automobiles now. They're all computers. So where there's computers, there's sensitive data that's moving. That needs to be secured at a high level. So that's a big factor. Of course, telecom is there. I would say technology and SaaS providers. And then, of course, one of the bigger ones is critical infrastructure, where certainly, we're able to get into, SCADA environments where we can be a bump in the wire, if you will, encrypting right off of a PLC. Going with data sensor data going to an HMI, and we can do this in, the very low threshold of relay time, which is only 4 milliseconds. We're well within that threshold to encrypt, decrypt, and we can do it with the same schema that I just discussed previously.
Yeah, SCADA is a good point because that somehow falls off. People don't talk about that enough when it comes to post-quantum cryptography. You heard it a lot when it was the IoT buzz, right? But then it kind of got quiet again.
Yes.
But people have to remember there's all these devices you're forgetting about out there. Once the post-quantum poop hits the fan, what's going to happen if we're able to just take control of all these?
And look, it can't be forgotten. I think it's been reported pretty widely now that, let's just say what it is. The Chinese have come into this country and they've set up shop. And, they're on our grid. They're on our critical infrastructure, whether they're inside or not. That's going to be the way they go about fighting wars, is going to be shutting things down and interrupting things. Who knows when, but it will occur. And they don't need to fire missiles and shoot bullets when they can shut down the grid or affect the grid. So this is not something to be ever taken lightly, and we need to do everything we can. That means public and private sector collaboration to work for these solutions.
And I know on the topic of war and all that, I know it's mainly classified, but what can you tell us about the military drone contract you guys received?
Yeah, so that is a convergence of current drone technology, adapting it for AI personas that will individualize each drone for whatever their mission or assignment is. And so there'll be AI involved. Some of these drones are actual suicide drones. I can say that much about them. And they will be, dropped from a mothership, thousands of them maybe, to go into their missions. And they'll have AI that will decide various things, whether to retreat, kill itself, and what to shoot, or reconnaissance and whatever it's doing. So our involvement is at the modular level, where we'll be involved in the drone operating system itself for security, and then the drone communications, drone to drone, mothership to drone, drone to ground station. Ground station could be just a militarized iPad, for example. and we'll be at a modular level. Now, one thing I would say that one of the reasons we're getting this is because the asymmetric use of cryptography is very complicated in that, as you can imagine, just because of the nature of the war theater or the environment. We're able to use that XSOC key, that large key, as a public key in that respect, as an analogy. And the TPM on the drone is actually the private key. So the TPM will have the authorized credentials in there, and when the data moves through the drone with the XSOC key and meets the TPM, then it will decrypt. Again, no overhead or latency issue, and that's how we'll have the security level. So we'll be at a modular level and through the various military drone architecture.
Yeah, you don't want to give some attacker the ultimate video game experience in the future. Right. These things need to be, part of the CIA triad for sure. So with us heading to Q-Day, everyone's worrying about mass migration, right? How easy is it to roll something like this out? And how crypto agile would it be going forward in the future?
Yeah, I mean, look, it's about having scalable architecture, and that's really, based on the performance and ability to integrate and be cross-platform, as long as there is, a place where data is ingressing and egressing, we can be placed. So, we're in Java now. We're going to also go to the Rust language, which is going to allow for even more performance, if you can believe it. It's pretty impressive, actually, and we can even be lighter weight. I mean, that's what new languages can do. And since the U.S. government is going to phase out the C language because of its security vulnerabilities now that are well known, Rust is one of the acceptable ones, and we'll be going to that. So that becomes very interesting. But scalability, because we have the performance, I mean, it's very adaptable and has all the agility components built in, so we could scale.
Great. We're going to have the website, obviously, in the show notes. Are there any kinds of demos available for companies if they wanted to reach out?
Yes, actually, we are also opening up very shortly here. In fact, there'll be a video of it, of our SaaS version of this, where we containerized that Java version, and will be available in AWS, so as a SaaS offering. So there will be a video of that, and I believe on the website there's a couple of videos of demos. They're a little techie because it's a command line interface, which is techie, but we do have that. But there's lots of resources on there. We do have some white papers as well, lots of information available, and anyone can reach out and request further information. And we're always happy to provide a live demo as well.
Awesome. Yeah. I can't think of a better way to end than that, I suppose. So if you're interested and you want to take a look, you can see it and maybe even have something interactive.
Absolutely.
So Richard, thanks so much for coming on.
Hey, thank you very much. It was a pleasure.
Now it's time for Coherence, the Quantum Executive Summary, where I take a moment to highlight some of the business impacts we discussed today in case things got too nerdy at times. Let's recap. XSOC relies on strong symmetric encryption at its core. Although symmetric approaches are normally thought of as encryption for data at rest, they can also be used for data in transit if keys can be securely sent. XSOC has a fast way to do this, allowing even encryption of streaming 4K video. XSOC uses a hybrid of stream and block cipher techniques with an expandable key space ranging from 512 to 51,200 bits. This allows for high levels of encryption if data has to be stored for decades, for example, without a need to re-encipher in the future. XSOC initializes in less than a millisecond, and the company says its encryption and decryption speeds are 10 times faster than AES-256. Keys are distributed and rotated with a unique zero-trust system. XSOC has FIPS 140-2 certification and was selected for a military drone classified project. We all have to migrate to PQC ciphers. I view this solution as an extra layer for critical environments. That does it for this episode. Thanks to Richard Blech for joining to discuss XSOC. And thank you for listening. If you enjoyed the show, please subscribe to Protiviti's The Post-Quantum World and maybe leave a review to help others find us. Be sure to follow me on all socials at Constant Hacker. That's Constant with a K, Hacker. You'll find links there to what we're doing in quantum computing services at Protiviti. You can also DM me questions or suggestions for what you'd like to hear on the show. For more information on our quantum services, check out Protiviti.com or follow Protiviti Tech on Twitter and LinkedIn. Until next time, be kind and stay quantum curious.